Here's a video about problem 14 from section 6.2 on the online homework. There were two problems at the end of the online homework for 6.2. One was number 12 and one was number 14 that each had parameters in them and asked questions about the result from the parameter. The purpose of those questions is that as we get into the part of the course about sequences and series, it'll be very common for us to have more than one variable running around in a problem. The x's will mean something and there will be n's that mean something. And then, of course, for those of you going on to Calculus 3, there are lots of variables running around and lots of problems there. So part of this is to give you a little bit of a problem-solving exercise, and part of it is to get you used to thinking about problems that have parameters. That being said, number 14 could just as easily have been a Mathematica assignment, because if you really roll up your sleeves and do this by brute force, the calculations are a little bit harrowing and maybe more appropriate for a computer algebra system. But let's run through it so you can see what the answer is. I'll try to give you an indication of the brute force way, but I'll also try to give you an indication of how you can use a little bit of intuition. So the question asks us to think about a parabola and a line, but the line has variable slope. So it asks us to think about that for various values of a, and then asks us a question about how to make the region between the two curves have minimum area. So they really are asking you to investigate this with some different values. So I've done that here, and I've actually included the areas, and I just used some whole number values of a that were small. And you can see of the ones that I generated, the one with slope -1 here is the one that has the least area between the curves. Now I'm cheating a little bit because I'm hiding in these pictures, I'm hiding the fact that it really was not that easy to figure out what the intersection points between the line and the curve are. In each case, it required the quadratic formula to figure out exactly how to draw this picture. So that's kind of a clue that the general calculations are going to be a little bit of a mess. But given that, we can just set up the problem. So the area, we know that the area is going to be given by the integral of the equation on the top, which is ax plus 3. And we're going to subtract the equation of the parabola. And I'm not going to go through all the steps of thinking about rectangles and so forth at this point. By the time you get to number 14, we should be in this position. And then the limits of integration are the kind of tricky parts. And so I'm just going to write R1 and R2 here just to stand in, and we'll figure out what those are, but they're a little bit complicated because of the quadratic formula, so it's hard for me to write them on the screen. But this is going to be the integral that we have to do. Now, when we do this, it's going to end up, there's going to be an answer that comes out in terms of a. So there's going to be an a left in the problem because the parameter a is just treated as a constant in all the calculations. That expression in terms of a is something that you can actually use calculus to figure out where it's a minimum. Namely, you can take the expression of a that comes out of this thing, you can take the derivative, set it equal to 0, solve for a, and that will be the the correct value of a that makes the area minimum. And I'll show you what the answers to the pieces of those are, but let me also try to give you some intuition for what's happening here. So the first thing is the integrand, if we simplify it, and by simplify it here I mean multiply this out and combine like terms. I'm just going to go ahead and do it. If I simplify it, I get 15 plus a plus 1x minus x squared. And I'm writing it that way because I want to see it as a quadratic. Now that's the thing that I would set equal to 0 and use the quadratic formula on to find my R1 and R2. So I'll just make a note that that R1 and R2 are the numbers that make this 0. And so I'm really in a situation, if you think about it, where this is a parabola. Again, it's a parabola with a parameter, so it'll be different parabolas depending on what a is. And these are the two numbers that reflect the x-intercepts of this parabola. This is a downward-facing parabola, and these are its two x-intercepts. And so this is really just an integral that represents the area under a parabola between its two x-intercepts. The only reason I mention that is because if we think about what those look like, we can actually use our intuition to figure out what the minimum output of this thing is going to be. So let's look at a few examples of this parabola starting and ending at its x-intercepts. I put them on the next slide, and I use the same 5 values of a that I used here, and you'll see the same areas come out. But the parabolas that we see on the other side, of course, are facing the other way. So the 5 things at the bottom of the screen there are the 5 parabolas that I would get when I'm doing this integration problem. The integral between the two x-intercepts of 15. What did I say it was? I should never turn the page before I write down what I'm doing. So the integral of this parabola between the two x-intercepts would look like these things. And again, you can see that the areas are the same as they were before, and so this is the one that has the smallest among the whole number value. So if the smallest is a whole number value and it's small, then that's probably it. But we don't know that for a fact. So we have to figure that out. The other thing intuitively about this particular, and I guess I could just say here, no, let me just go ahead and do what I was going to do. The intuition here can be pushed a little bit further because the fact that this is x squared means that this parabola, there's no scaling that's happening with the parabola. All of these parabolas are just copies of y equals x squared. That's all those are. So every one of them is a version of y equals x squared that's been flipped over and translated up and to the right a little bit, or whichever way, translated up a little bit. But there's no stretching or scaling. There's no multiplying by a number, by a y value. So this thing's not being stretched. So it's literally just copies of this thing that are being flipped around. The reason that's important is to realize that these all are really the same parabola. It's just that their position is different. So they're being moved around based on the value of a, but there's no scaling. And so the intuition is that the version of this that will have the smallest area is just the one that is the lowest, the one that's closest to the x-axis. That's only true because there's no scaling going on here. Every parabola here is identical, and so the parabola that is the lowest is going to have the smallest area. That's actually a much easier question to figure out which parabola sits lowest on the paper, because it doesn't involve us doing an integral to answer that. So both to see how that would give us the answer and also to save us some trouble with the integration, I'm going to do one more step with this integram, and I'm sure everybody's going to moan when I say this, but it actually helps a lot in this case to rewrite this in its vertex form, which is equivalent to completing the square. So rather than standard form, if I write this in its vertex form, I will have, I already did it, so be 15 plus a plus 1 over 2 squared. Get rid of this. Can I get rid of that? I can't get rid of that. Good grief. Minus x minus a plus 1 over 2 squared dx. The advantage, and so the advantage of this is that means I can identify the vertex. So the vertex is always given by coordinates a plus 1 over 2, comma, 15 plus a plus 1 over 2 squared. So if you believe that the lower this is, the smaller the area that it can enclose, then it's actually really easy to see that the lowest that your vertex can be, this is how high your vertex is, the lowest that can be is when a equals -1. It's 15 plus a plus 1 squared. So the smallest, the square part can be a 0, and that would happen when a is equal to -1. So the vertex is lowest when a equals minus 1. So that's the cheapo way to see what it's going to be. And again, it only is true because all of these parabolas are identical. They're just shifted differently. If there was any scaling at all, if they were being squished or stretched at all, then we wouldn't be able to make that conclusion. Okay, so the reason I did complete the square is not only because it makes that obvious, but also because that actually makes it pretty easy to find these roots. The limits of integration, if you do want to stick this in Mathematica, and you want to do this integral, your roots are going to be in other words, one of the other reasons that completing the square or using this form is useful is because it's very easy to see what your x-intercepts are. The x-intercepts are just this number, the thing that makes this 0, plus or minus the square root of this. So those are my limits of integration. And the rest of it would look like this. So this is the integral that you would have to complete in order to get the area as a formula in terms of A. And it's not entirely unreasonable. It's not a hard integral in this form because the antiderivative of this is just with an x, and the antiderivative of this is just 1/3 that cube. So I would not multiply it out. Leaving it in that vertex form is really the right way to do it, no matter what. But obviously, once you do that, then plugging the limits in can be a little bit hairy. It does come out to be a reasonably nice answer. It simplifies a lot. But what you will end up then is a formula for the area as a function of that little a parameter. And so if you really want to stick to brute force calculus, you would take that formula, take its derivative, set it equal to 0, and solve for a. And what you'll find, and won't be surprised, is that a is -1 in that case as well. So that's how you do it. I know that's it's a complicated problem, but hopefully you'll gain some insight not only into how integration works, but also with using parameter in a problem. I would recommend you watch the video for number 12 as well, because that has the same philosophical advantage of thinking about parameters, but also does not have nearly as bad computations. So it's not quite so scary.